All right, here we are with part two. What happens when waves approach the shore? And remember, we're talking about wind waves here. The other waves that we talk about will be much larger than this. So wind waves are the waves that are going to make the transition from deep water waves, which is what you see on the left, to shallow water waves, which is what you see on the right. So remember, a deep water wave means that there's plenty of room for all of those orbital circles. A shallow water wave, as you can see on this diagram on the right-hand side, the circles are kind of flattened out. There's not enough room for all that motion. So that's what happens to waves as they approach the shore. And if we want to get more specific about what happens to these wind waves, when they reach a depth of about 1/2 the wavelength, they touch bottom, and that causes the orbitals to flatten out. The wave crests are also going to become taller, so we actually see an increase in wave height as the wave tries to accommodate or make room for all of those circles. So they flatten out, but you'll notice that the stack kind of moves up and gives us a taller crest. As it gets even closer to shore and the water gets more shallow, it just gets too tall. And remember, we have that 1/7 ratio that we have to maintain, and if the wave gets taller than that, it will break. And so that's what you see on the right-hand side of this, is that the waves break, we lose our circles, and if you go online and look at videos of breaking waves, you'll see that circular motion, and then once you get close to the shore, you can see we've really leveled things out, and the water kind of moves back and forth in the surf zone. So that's what happens to our wind waves when they get to the shore. They get taller, the circles get flatter, and eventually they will break. So let's talk about some other things that waves do. And these are not just wind waves. All waves will do these things. So number one is wave refraction. That is shown on the left. When the wave slows down, as it touches bottom, you'll notice that it will turn. So if you look at the blue line as a wave crest, when one end of the crest slows down compared to the other, the wave will actually turn. So waves tend to turn or bend toward the shore. And this effect will also can be seen on tsunamis when we talk about those in a little bit. When waves pass an island, the side or the end of the wave that is next to the island will slow down, so the whole wave will bend around the island. And you can see that effect on this little island here. And then on the back side of the island, we now have two sets of waves that are going to be able to interfere with each other, and that produces a pattern that we call diffraction. One of the interesting things about diffraction is that the Polynesian navigators, if you remember those stick charts we looked at in chapter 2, they were actually able to recognize these diffraction patterns and use them to help them navigate to islands that they couldn't see. So this pattern where two crests meet, for example, you would get an extra high crest where a crest sits in a trough, the waves will temporarily cancel each other out. So if we go back to the wave interference pattern, these patterns will set up where these wave sets interact with each other. So now we're going to talk about a few other things that we see. Some of these are going to be waves, some of them are not. This first one is not actually a wave. A storm surge looks like a wave, but it's not. We do not have the circular motion of the water. What a storm surge is, it's actually a bulge of water. It's a short-term rise in sea level that moves with a large storm. And you'll notice on this diagram underneath the storm is low atmospheric pressure. That low pressure allows the water under the storm to rise up because there's less pressure pushing down on the ocean surface than in the surrounding area. The other thing that happens with a storm is you get a constant wind. And as the storm moves, that wind is all pushing in the same direction. So if you put those two things together, the constant wind plus the low pressure, you get a dome of water under the storm that moves with the storm. And as the storm gets closer to the shore, that water gets pushed up onto the shallow seabed and creates what we call a storm surge. And storm surges can be anywhere from 1 or 2 feet to as many as 5 or sometimes 10 feet or more, depending on the size of the storm, the strength of the wind, and how low that low pressure is. And really, rather than think of it as a wave, it's better to think of a storm surge as just a temporary rise in sea level that comes with a storm. The next kind of wave is kind of an interesting wave. It's called a seiche. A seiche has a wavelength of 2 times the width of the basin that it's in. It is a rocking wave within that confined basin. You can make one of these yourself. If you fill the bathtub about 1/3 full of water and hop in, well, actually sit in, and then slowly start moving back and forth, you can get all of the water moving together, and that is what a seiche is. These do not happen on the open ocean. They happen in an enclosed basin like a bay or a lake. The example they give in your book is actually in Lake Erie. In that case, the wind was very strong and sustained with the storm and actually pushed water. Essentially, a storm surge occurred at one end of the lake, and then when the storm passed, the water came back, and that is what set that seiche in motion. An earthquake rocking the ground can create a seiche as well. The trick with the seiche is you've got to get that rocking motion, and the wavelength has to be 2 times the width of the basin. A tsunami is one that you've probably heard of. Tsunamis are very interesting waves. They are caused by the rapid displacement of water. And this can happen with a very large landslide, or more typically what we see is fault movement under the ocean floor. And in this case, the fault or the ocean floor actually has to be displaced. Not all earthquakes that occur under the ocean will include a tsunami because they don't all move the ocean floor in a significant way. So what happens is this bumping of the ocean floor generates a wave that has a very long wavelength, 75 to 125 miles. And if you remember our classification, that makes this a shallow water wave because half of the wavelength, even for 75 miles, is a lot more than 2 miles. So tsunamis always behave as if they're in shallow water. There is not enough room for all of their circles, so their circles are very flat in terms of their wave orbitals. On the open ocean or the deep ocean, the height of a tsunami is only 1 to 3 feet. They're very short, and with these long wavelengths, if you were in a ship on the open ocean, you would not notice the tsunami going by. You just wouldn't. They're too short and the wavelength is too long. However, when they get close to the shore, that water essentially ramps up on the continental shelf, and it can build up very dramatically. Tsunamis of 3 to 30 feet are common for tsunamis, and in some times and in some places in the past, the waves have built up to be as high as 100 feet. And this has to do, how tall it gets, has to do with refraction and diffraction, all right, the interference of the waves and how they behave when they approach that shoreline can make them quite tall in some places. And the effects are felt most noticeably in harbors And the word tsunami is Japanese for harbor wave, which is where you don't want to be when a tsunami comes in. Now, the other interesting characteristic of the tsunami is how fast they go. On the open ocean, they can travel 400 to 600 miles per hour, which means they can cross the Pacific Ocean in 12 hours or less. And when they approach the shore, they slow down as any wave would, but still they approach the shore at 50 to 70 miles an hour. So this is not a wave that you can get out of the way of. One of the interesting effects that people notice is that very often the trough gets to the shore first, and so the water goes way out. If you were standing on the beach, you would see the ocean floor exposed, and then that crest comes in at 50 to 70 miles an hour, and if you were just watching that exposed ocean floor, there would be no way for you to run away from that. People that live in areas that are subject to tsunamis, one of the things that they learn to do is if they see that trough approach, if they see a lot of ocean floor exposed, they know they have just a few minutes to run for high ground. So this is the Japanese tsunami of 2011. You can see it was triggered off the coast of Japan by the movement of a fault on the ocean floor at a subduction zone. Some of the waves went across the Pacific. They hit California in about 12 hours, and they got to the nearest coastline in only about 15 to 20 minutes. So that's these right here. This was generated very close to the shore, so it didn't take long for those waves to get to the coast. And this shows the travel time going across the Pacific Ocean. You can see California in about 9 to 12 hours, and South America within about 18 to 21 or 22 hours to get to the coast of South America. So they're very, very fast and can be very destructive. Now, when they get across the ocean, the energy is usually dissipated, so they're not as tall. At the coast of Japan, some places had 30 feet of water coming on shore. The coast of the United States generally experienced the tsunami as a 1 or 2 foot wave. There were some places along the U.S. coast that experienced a wave that was about 3 or 4 feet, just because of the shape of the coast focusing the wave as it bent. And so that is it for this part 2 of waves. Part 3 will be a discussion of the tides.